Now, what this means is that the dilation is actually going to be quite high if you're using the associated flow. Using the non-associated flow rule, then you can choose whatever your dilation parameter is, but then how do you parameterize it? There's lots of people who are doing experiments, but this is still mostly in the research realm. For the application, the commercial realm, some good rules of thumb are that soils and very weak rocks have very low dilation. A lot of it having to do with compactant type behavior. If the porosity is very high, the materials will tend to compact, so they won't tend to dilate so much as they're shearing. So we can say that the dilation will be something bigger than 0, but much smaller than, for example, the friction angle. For strong rocks and some strong soils, the dilation will be larger, still less than the friction angle typically, but maybe approaching what the friction angle is. So this is somewhere in the non-associated, associated flow rule. So for very brittle rocks that tend to have a considerable amount of dilation when they break, or for example, some clay soils that dilate, or some densely packed sands that dilate when they shear, then approaching the associated flow rule might be a more appropriate method. So hopefully this has broken down a little bit about the uncertainty about dilation. This is a parameter that we're not really used to parameterizing in our typical soil mechanics, rock mechanics courses, but is a parameter that we have to put into our numerical model, especially if we're expecting plasticity. If we're doing an elastic model, we don't even need to think about dilation. But if we're expecting plasticity, then we need that dilation. Okay, so now we're coming to the last bit of our fundamentals. So we've covered the mathematics, the stresses, a quick overview of constitutive models, focusing mostly on post-peak behavior. Now I want to talk about code types and selecting our code types. So this is sort of the segue into starting to use our engineering judgment, is our modeling approach. How do we select the best model? Generally, most continuum models are formulated using the finite element or finite difference method. There are other methods, certainly, but those will be the two most commonly used methods. And nowadays, despite a lot of the lingering mythology around finite element, finite difference, the solutions and the controlling and a lot of the benefits and weaknesses of each method, they've learned a lot from each other. And that's allowed them to sort of normalize the way that they function, where some of the things that historically were true of one and not the other are now essentially true of all of them. So nowadays, finite difference, finite element, those are mathematical aspects of the code, but from a functional perspective as an engineer, it doesn't really matter whether you're using finite element or finite difference. So some of the bigger considerations then are having to do with the different types of models rather than the solvers that they use. So two of the most commonly discussed types of models will be continuum versus discontinuum. Which one do you pick? So let's have a look at how the response, or how each of these are formulated. A continuum model treats the material as an equivalent continuum. It is built out of a mesh, and the function that would describe its displacement at an excavation boundary, for example, would be a smooth function, or relatively smooth, of course, because of the discretization. Discontinuum, on the other hand, treats the material as a series of blocks, and those blocks are separated by joints, by breaks, and all of the action happens on the joints. Now, a lot of discontinuum models also allow a continuum model inside, so a finite element or finite difference model is applied to the inside of the blocks, but the joints, the discontinuities, the separations between the blocks have a lot of action happening on them. And so if we look at then the displacement of an excavation in a discontinuum code, we would see that that displacement would be more stepwise, associated with the discrete movement on each of these discontinuities. So another way to visualize this is to think about a rectangle of rock or a cylinder of rock that is being applied a stress in the axial direction. In the continuum method, that material will then deform axially and also laterally, according to Young's modulus and Poisson's ratio, but form a continuum, so some sort of barrel shape. And if we looked at the displacement, if we took a line down the center of this barrel and we looked at what the displacement at any point was, we would have a smooth function. A similar rectangle of rock or cylinder of rock with a discontinuity through it, if we were to apply a force or a stress across the top of that material, the deformation at the top would be in the downwards direction, but actually this top portion is deforming, is sliding down this discontinuity. And so if we then took a line down this material here and plotted the deformations, we would see that this entire block has moved downwards an equal amount of distance at any point here, and then across the discontinuity, we switch to the bottom block, which has not moved at all. So this is our discontinuum type displacement. And this then is linked to the type of behavior that we're expecting. And making our decision between continuum and discontinuum then has to be led by the behavior we're expecting in the problem that we're trying to solve. And a nice way of visualizing this then is to look at a matrix of excavation types in different types of material. Let's focus on rock, for example, and different magnitudes of stress. So shallow tunnel in massive jointed or heavily jointed would require continuum, a discontinuum where wedges and blocks falling out of the crown are important, and where rolling is important, is highly rock mass, we would probably want to solve it with both types to look at answering two different problems. Under high stress, the massive material is still a continuum problem, that's fine. The jointed material now turns into possibly we might have some joints falling, possibly we might have some stress-induced failure. So both modeling types would be appropriate. And then in the heavily jointed rock mass, so if we picture a very heavily jointed limestone under a 2,000 meter mountain, then we're going to be expecting more like squeezing type ground rather than raveling. And that can be approximated using a continuum method. So then linking the problem that we have, the type of conditions that we have, and the behavior that we're expecting is super important for selecting our approach. That being said, even within continuum codes, it is possible to put in discrete joints and joint networks, and they work a little bit different than discontinuum codes. They're computationally quite expensive. They really slow down a numerical model, but it is possible. The deformations along these discrete planes will be calculated, but the mesh is still connected. It's still a continuum mesh, so we can't have very high displacements and we can't have opening across these joints. It'll demonstrate movement, localized movement associated with the joints, but it won't actually show us any sort of opening behavior. We can't have this little piece of rock actually fall out of the mountain, for example, like we would with the discontinuum code. But there are some capabilities for implementing discrete joints, which can be useful even using a continuum model. Another way of dealing with joints is using ubiquitous joints. And this is a non-intuitive method of thinking about it, but the way that ubiquitous joints works is that it solves the constitutive model of an element twice. The first time it will solve the constitutive model, so failure or not failure, inside the element based on its failure criterion. So Moore Coulomb, generalized Hooke-Brown, Drucker-Prater, Cam-Clay, whatever it is for the material, it will solve to find out if that element has failed or not. Then it will solve a second time on a plane. So it'll solve the normal and shear forces on a plane to see if that plane has failed. And if that plane has failed at that particular angle, then it will say that that element has encountered planar failure on the ubiquitous joint. So there are no discrete joints. Each element is solved twice for the continuum part and at a certain angle. And what we will then see is little notations of failure throughout the elements. And this won't necessarily lead to shear displacements along a joint because there's no discrete joint. It's only just a test. It's a constitutive model test at a certain angle. So that's different from this type of model where we can actually demonstrate shear deformation on a discrete location, a very specific location. This model will not do that. But it is still an important method and a very rapid method for seeing if joints are an important component of the behavior of our material. And then finally, discontinuum models, fully discontinuum models where we have the blocks. They're related by some normal and shear stiffness, and the blocks can actually move with respect to each other. Discontinuum models are formulated in such a way that, for example, this block could actually fall out of the mountain if that was kinematically feasible. So it helps us to answer a completely different kind of question. It would help us answer if we have movement on this specific discontinuity, and it can also demonstrate large strain type of behavior. So then moving on from discontinuum versus continuum, thinking about the dimensions of our model. So for a lot of problems that we're trying to solve, for tunnels, for strip footings, for retaining walls, plane strain is appropriate, like we talked about earlier. But sometimes for our tunnels, we're interested not just in what's happening around the circumference of the tunnel, but also what's happening in front of the tunnel. What's happening in front of the face can be also very important, especially in weak rocks or soils. And in this case, the plane strain model is not useful. We need to be looking into that third dimension. So there's two possible solutions. One is a full 3D model. The other is an axisometric model, which is a 2D representation of a three-dimensional problem. And for an axisymmetrical model, it's valid for a symmetrical problem. So a problem that has one long axis, so for example, a triaxial sample, and is symmetrical in 360 degrees, so a cylinder. And that is actually quite appropriate for most of our tunnels. We can simplify most of our tunnels and say, sure, they're more or less circular, and they have this long axial direction. So what we do then with our axisymmetric modeling is we take this cylinder and inscribe it on a plane. And what we have left in this inscription is a rectangle, and essentially we have an L-shaped model. And this little GIF over here shows us in 3 dimensions what that little L-shaped model might look like that represents this cylinder. And when we set up our axisymmetric model in a numerical modeling software, then we have this L-shaped model where this is the tunnel face and this is the tunnel wall. So it's a little bit unintuitive in terms of how it represents the tunnel, but this allows us to then see the deformations in the face and the deformations in the tunnel wall. So this is a nice way then, if you only have access to a 2D numerical modeling software, or you don't have the resources in your project to go to a full 3D model with all of its complications, this is a nice way of looking at tunnel face behavior using a 2-dimensional model. So then the modeling strategy, make a decision on what type of model that you're going to be wanting to use. So if you're using continuum model, do you want to use an elastic solution? Are you only interested in the stresses, or maybe comparing the stresses to the strength, looking at a strength ratio or a strength factor? Then an elastic model might be useful. If you're interested in looking for failure and actually causing failure and dilation of your material, then you need a nonlinear model. So this is a model that's capable of using plasticity. If you think that it's going to be movement on discrete joints, you think that maybe blocks are going to be falling, or you're going to have sliding on a particular set of parallel discontinuities, then discontinuum modeling might be useful. Using realistic blocks that can put in a nice discrete fracture network, or using a particle code, although commercially for tunneling applications, that's not really that common. And then from a research perspective, there's lots of really cool hybrid models that are coming out nowadays that allow fracture generation. So in discontinuum model, you actually have to put the fractures in at the outset. A hybrid model allows those fractures to be generated as part of the constitutive model examination process. And then there are other types of hybrid models that allow combinations of finite element, discrete elements, or finite element, finite difference, and heat or water models that are joined together. So those tend to be more so in the academic sphere. And then, of course, there's what the dimensions are for most of our problems. Plane strain will be fine, but sometimes we're interested in that third dimension. So it could be that an axisometric model is sufficient. It could be that we have to move all the way to 3 dimensions. So the selection of our tools will then be based on the magnitude of stress, so how deep our tunnel is, the rock or the soil strength, if we're dealing with rock, the integrity, so how fractured is it, the scale of our problem, the complexity of our problem, and the availability of our code. So the reality in most design offices is that a design office will buy a code, maybe they'll have Plaxis, or they'll have FLAC, or the Rock Science Suite, whatever code it is that they have, and that's the code that you have available. So a lot of times you're trying to find a way of modeling your problem using the codes that are available, but it's important to recognize that if the code that you have available is not appropriate, then there's not really that much value in using that code, even though you think, oh, we have to do numerical modeling because we have to show the client that we're doing this, and we have to show the pretty pictures and show that we're really cutting edge. If you're not using the right model, simply because that's the one you have available, then you're not actually adding value to your client. And actually, it could be the opposite. You could be devaluing and taking time away from using a method that would be more appropriate to the problem. Away from the fundamentals and moves us towards then using our engineering judgment. So selecting our code is sort of the first step in using our engineering judgment, linking the tool that we're going to use to the problem we're trying to solve. Now, once we've selected our tool, we need to start building our model. And building the model requires a series of steps. And again, at each step, we need to be thinking, how are we going to do this? What is the best way to represent our problem in the most appropriate way? And so there's sort of, I've broken this up into sort of 4 steps, and they form a circle, a cycle, where we'll just look at the 4 steps independently, but normally you would go through these, and once you've gone through a cycle, you might be changing the model and going through the cycle again, and change the model and go through the cycle again, over and over and over again, until you're happy with the results that you have. And then you can use those results to create your design. So we're going to look at each of these 4 steps one after another. So the modeling setup sequence, there's not really an officially out there modeling workflow, but I've kind of put together a workflow that is reasonably straightforward, sequential, and touches on the most important aspects of building up our model. So those can be sort of broken up into 2 bits. So one is how we set up the model itself, and then the next is considering some of the setup that has to do with how we run the model. So first up is the geometry, setting up the geometry of our model, where our boundaries are going to go, what does the geometry of our excavation look like, etc. So this would be an example of a deep tunnel. We're not at ground surface here. So for a shallow tunnel, this could be a free surface demonstrating ground, or if for a deep tunnel, we can have just some excavation boundary. This demonstrates the mesh. This is an automatically generated mesh in RS2. And this is our excavation. So in this case, I'm using a very simple circle to demonstrate our tunnel, but it might be that we want to build a horseshoe cavern, for example, or whatever other shape, a square shape mining adit, whatever the shape is, we should represent that shape as well as possible in our model. And nowadays with AutoCAD exporting a DXF, that's reasonably straightforward. The rule of thumb for establishing our external boundaries is for those external boundaries to be a minimum of 3 diameters away from the boundary of our excavation. And that's one that's pretty much universally discussed by everybody. Oh yeah, the 3 boundaries, 3 diameters away. And mathematically from an elastic model, we can look that makes a lot of sense. If we're doing a hole in plate Kirsch solution, analytical solution to the stresses around a tunnel, most of the stresses reduce back to the in situ stresses after 3 diameters. However, if we have a plastic material and we have to be redistributing our stresses, that could actually push our stresses further out. So this is a minimum of 3 diameters away. It's not a set rule that it has to be 3 diameters away. This is a minimum. It can be, and oftentimes should be, further away. I'm showing here a square grid because oftentimes it's nice to think about a square grid, especially if you're applying your own stresses or forces on the boundaries. But there's no reason not to use a circular grid, for example, for a circular tunnel. So this is an example here from Rock Science in RS2 showing a circular tunnel. This is in an isotropic stress state, so sigma 1 and sigma 3 are the same, and showing what the elastic stresses around that tunnel are. That's great. So why not? Most of us aren't used to looking at models that look like this, but mathematically, there's no reason why the grid, the external boundaries have to be square. At least not in Rock Science. In other models, for example, in FLAC, a square external boundary makes a lot more sense because the grid is normally square, but Rock Science uses an automatic grid generator, so it doesn't really matter. Something else to consider is this concept of distance from the excavation boundary. So what I showed earlier was the rule of thumb, which is 3 diameters away. So this is how many diameters away from the excavation boundary. So this is a log scale, 1, 2, 3. For an elastic model, when we have 0 plastic radius, no plasticity in our material, 3 diameters away is reasonable. As our material becomes weaker, our plastic radius increases, we also need to push our model boundaries further away. And the reason that we have to do that is if we come back and look at this model here, oftentimes weird things are happening with the stresses, especially at the model boundaries. And the reason is that there's a mathematical solution to the stresses in this element, and there's no way for the stresses and the displacements on these nodes to be shared in this direction. There's a mathematical solution here, which is fine, but it's not a true solution as though there was a material here. And so oftentimes corners will be a little bit funny. So we want the corners to be as far away as possible from our area of interest. So we're trying to solve for what's happening in here. We don't want our solution in here to be affected by the funny things that are happening in here. And similarly, if we have a large plastic radius around our tunnel, our stresses are going to be impacted quite far away. And we don't want our stresses to be impacted and hit this boundary, because this boundary will not continue to allow the stresses to be redistributed out this way. We'll just stop the stresses. So we could end up with some weird stresses happening here at this boundary if our plastic radius is too big. So we must make sure that all of the action, everything that's happening around here, is far enough from the boundary not to interact with it and mess up the mathematics. So this is why a graph like this shows us that we might be looking at an excavation boundary that's 20, this looks like it's about 25 diameters away for a very large plastic radius. I mean, this is 10 times the radius of the excavation itself. So very, very weak material, very large plastic radius. But this is just to demonstrate that that 3 diameters rule of thumb is an absolute minimum, and that's based on the elastic solution. As soon as we have plasticity, you should be thinking about putting your boundaries further away. For an axisymmetric model, this would be the same thing, right? Here is our tunnel, and here we have probably about 10 or 12 excavation boundaries, diameters distance for our excavation boundaries. It looks a little bit funny, our tunnel is so tiny, but if our material is very weak, then that's important, because if we have a lot of action going on here, it might interfere with our boundaries if our boundaries are too close. Now, speaking about boundaries, boundary conditions and meshing. There's a couple of things to consider for both the axisymmetric and the plane strain method, as well as any three-dimensional method, is that fixing the boundaries in space is super important. Otherwise, our model will start moving in space and we won't actually generate stresses in the material. So we need to be fixing these boundaries. And that's also part of why the boundaries need to be far away, because if we have deformations in these elements here, they can't move along this boundary. So that's going to cause some weird strains in the corners of these elements here. So we need these fixed boundaries to be far enough away that they're not being impacted by deformations. So for this sort of setup where we have a deep tunnel and we have an in situ stress condition that's applied to the material, we can have fixed boundaries all the way around, or we could do roller boundaries all the way around. It doesn't really matter. For an axisymmetric model like this, we can have a fixed boundary way out here in the back. That doesn't really matter. Fixed or roller boundaries up here at the front. But what's absolutely critical is to have roller boundaries on this end here and roller boundaries on this end here to allow those deformations. We want the tunnel to be deforming into, we want the material to be deforming into our excavation boundary. So this needs to be able to roll in this direction. And the face needs to be able to deform into the tunnel. So it needs to roll in this direction. And the reason I say roll is that the way that we visualize boundary conditions is using these little roller notations. So this roller is as though we had a bunch of pins or logs that allowed this material to move vertically. So it's rolling, and this material can move horizontally, again, as those rolling. This material with the triangle here is not allowed to move in any direction. This is a fixed boundary. So this is common boundary condition notation, these little triangles and these little rollers that demonstrate no movement and movement in the X direction and movement in the Y direction. The second thing to consider then is our discretization and our mesh. This is a great example showing how the mesh, the mesh size, the element size actually changes. And this is a way of simplifying our model, reducing the computation time. On the outside, way out here in the boundaries, if our boundaries are far enough, whatever is happening here, we don't care, because it's not important to our problem of interest. So we can have reasonably large elements out here because we don't need precision, we don't need accuracy. We just need this to be preventing weird mathematical things from happening. But closer to our excavation boundary, we're actually really interested in what's happening here, often at the millimeter scale. So our elements need to be small enough to capture those small amounts of deformations and to have a good precision for the changes in those deformations with space. If our elements are too large, then the amount of change that we'll have over a certain area will be too big and won't give us the amount of detail that we want for our design. So a method then is to have a coarsening mesh where the mesh is coarser near the excavation boundary. A fining mesh where it's finer near the excavation boundary and coarser near the external boundary. And we can see that in this plane strain model as well, where we have a finer mesh right around our excavation boundary where the action is happening, where we're interested in precision, and we want the mathematics to be detailed. And out here we have large elements where the mathematics can be less detailed and it doesn't require as much computation, because the computation of a numerical model has nothing to do with the scale of our problem. It has everything to do with the number of elements. So we're constantly trying to maximize the number of elements for the amount of detail that we're trying to achieve. All right, so the next decision we need to make then is our materials. How are we going to represent our materials in the model? Normally we'll have some sort of geological model, geotechnical model that tells us where different materials are, and we have to make decisions then. This, for example, is a bedded material, so sandstone, siltstone beds with the bedding planes here modeled as discrete joints. So this is a continuum model. This is a finite element continuum model, but it allows discrete joints, so we can model the bedding planes as joints. And then inside here, we can have this as sandstone, we can have this as siltstone. And the level of detail then that we put to our geology depends on the scale of our model, the amount of detail that we're willing to compute for. So do we want to have very thin interbeds of siltstone in our sandstone here? Is that important? Is that an important component of the behavior that we think is going to happen? If so, then we should include them. If not, then we can sort of make an average continuum sandstone with siltstone interbeds, and we have to choose then how to represent that as more Coulomb or Hooke-Brown material. What sort of strength parameters do we put into there? And we then have to decide, do we want to use a more Coulomb or a Hooke-Brown failure criterion? Or if we're looking at soils, are we going to use a cam clay or a viscoplastic? What sort of constitutive model can our code handle, can our software handle, and what is most appropriate for the material that we're trying to model? Are joints important? So in this case, these are the bedding planes, they're important. If we look at a different kind of material, for example, here, maybe this is a limestone with limestone beds and then perpendicular joints. Lots of software nowadays, continuum software, is coming up with the ability to do joint networks, whether it's regular joint networks like these that are perpendicular, or these that are orthogonal to each other, or Voronoi joints, which are these here that represent a more random orientation of joints. Whatever those are, then there are some abilities to represent these key parameters. Now, keeping in mind that if this is a continuum model, we won't have separation on these joints. This is only going to allow the model to displace and strain in the direction of these joints. And for example, in the direction of these joints. And the continuum model will never be able to break across this intact material that's between these two joints. So this rock bridge here will never break and will never get deformation across these two joints. You need a hybrid code for that. Yeah, but it still gives us a good method for taking into consideration discrete joints. Now, of course, if we don't want to be taking into consideration discrete joints, there are continuum methods for parameterizing a jointed rock mass. For example, the generalized Hooke-Brown failure criterion geological strength index. That's a completely valid way of representing a jointed rock mass without having to put in these discrete joints, which require you to know something about their orientation, something about their strength, something about their stiffness, and then additional computational effort. So these are all complexities that you have to think about very carefully when you're choosing your materials and how you represent those materials. Moving on from materials then is stress conditions. There are a number of different ways of thinking about stress. We can think about gravitational stress. This is essentially where all stress in the subsurface comes from. But in a numerical model, calling gravity means something. Or we can use in situ stresses, or we can use external and internal stresses. So one of the most commonly known concepts for all of us who are working in geotechnics is the concept of gravitational stress. So we're quite used to computing the vertical stress as a function of the depth and the density of our materials. Here's a generalized equation that we could use that's based on empirical data from all over the world. And then relating that to our horizontal stress using the K0 factor. So that's the horizontal to vertical stress ratio. And that stress ratio can be anywhere below 1 or above 1, depending on where you are, depending on what the tectonic conditions are, etc. If you're in soil, it's probably going to be closer to 1. If it's in rock, it can be all over the place. When we tell a numerical software to use gravity, rock science will do it, FLAC will do it. For example, we just say, turn gravity on, use gravity. It will take some plane of reference as the surface of the ground, and then we'll calculate the sigma v as a function of the density and the location of every element with respect to that surface. So it will give you a nice gradation of your increasing stress with depth. And then as long as you tell the model what the K0 factor is, it can also calculate what the horizontal stresses will be. So that's really great. That's a nice way of calculating or of inputting our stress condition for shallow problems where the model or the excavation is close enough to the surface that you can include the surface in your model without too much additional elements. Now, of course, if you're looking at a 2,000 meter deep tunnel, you probably don't want to model 2,000 meters worth of stresses. So you have to think about a different way of inputting those stresses. And in that case, what you would be doing is inputting your initial stresses. You would use an initial stress condition. And that would be some sort of sigma 1, sigma 3 if you're in plane strain, or sigma 1, 2, and 3 sigma 1, 2, and 3 for plane strain and three-dimensional stresses. The most important ones obviously being sigma 1 and sigma 3, your major and minor principal stresses, but sigma 2 can also be quite important. So don't just make it 0, because then that becomes sigma 3. You have to make it something. The orientation of the stresses, the major principal stress and the minor principal stresses, will depend not just on gravity, but also on the tectonics, especially if you're in rock. And it'll depend on what the tectonic history of your area is. Even if you're in a very stable craton, like parts of India, like North America, Australia, Africa, for example, even those will have not necessarily vertical stress as the maximum principal stress. And your stress magnitudes may not necessarily be exactly the gravitational stresses. If you're in an urban environment and you're doing a shallow tunnel, gravitational stresses are probably sufficient because it's the overburden that will be the controlling factor. But when you're looking at a deep tunnel, especially in an alpine environment, you have to consider the tectonics. It could be that if you're in a tectonically active area, like the Himalayas, that your major principal stress is actually horizontal because of the tectonics of the mountain building. If you're in an extensional area, so for example, in areas where we have a subduction zone, or there's, for example, rift areas. So the rift areas of Africa, here in Central Europe, we have the Rhine Graben. There's all sorts of places where the tectonics are actually pulling. So in that case, then we have very, very low horizontal stresses in the pulling direction. So getting a feel for those stresses, and there's lots of courses in site investigation and rock mechanics and soil mechanics for estimating those stresses. But it's important to not just use the depth and the overburden for sigma v when you're in a deep tunnel. You also have to consider if you're in an area with topography, again, in a mountain area, even if you're not in a deep tunnel, Even if you're just doing a tunnel that's punching through a shoulder of a mountain, for example, it's only 300 meters deep, the stress orientation is going to be governed by the topography. The sigma 1 is often parallel to the slope of a hill. So a tunnel punching through the shoulder of a mountain will not have the sigma 1 perfectly vertical. It'll be a little bit tilted. And that can be important for where our failure occurs, where our highest deformations occur, and how we have to create our design. So getting the stresses right, getting a good idea of what the stress conditions are, and not just using the weight of the overburden is really important, especially in more complex terrain. So once we've selected our stresses, then we have to do something called the initial conditions. So setting up the initial conditions for our stresses, whether that's by, for example, in the RS2 software, we can simply say what sigma 1, sigma 2 are. In this case, it's shown here in this little box diagram where sigma 1 is horizontal, sigma 2 or sigma 3 is vertical. So our highest stresses is horizontal, lowest stress is vertical. And then those are the initial stress conditions. We haven't excavated anything. We are just putting in what the stress in the rock mass is, or the soil mass, before we excavate. We can do it this way, or we can create our excavation and apply a stress on the excavation boundary that is equal to our in situ stress conditions. This is another way, and there might be some reasons why we want to do that depending on our solving technique. This method allows us to slowly reduce the stresses, and this becomes important in a minute when we talk about how we actually simulate the deformation and the decrease in stresses during excavation of a tunnel. But focusing just on our initial conditions, our initial stresses, this is really important. We have to put in the most appropriate stresses, and then we have to run the model. The model must be initialized to allow all of the minute deformations to occur, to allow, especially if we're using gravity, to allow the model to compute what the gravitational stresses are and allow any sort of movement. We visualize it as movement. Obviously, the elements aren't actually moving, but mathematically they are. They're shifting around a little bit during that initial solving, and that's just mathematical junk. We don't want that in our results. So we do this initial run, and here's an example showing contours of deformation, and we haven't done anything to our model yet. This is just numerical junk. We don't want that there. Of course, the magnitudes are tiny. They're not that important, but there are other conditions where they might be important, and we need to get rid of that. So we run the model, we initialize it, and then we zero the displacements. All software has some method for zeroing the displacements. In the RS2 software, it's a button that you have to click. In other software, you actually have to tell it to reset the displacement. So in FLAC, for example, there's a little piece of code that you would write that says reset the displacements, and it puts everything back to 0. So then you're actually in the true initial conditions. Your rock mass or your soil mass is as it should be with all of the stresses distributed properly, but nothing has moved. And then you can start excavating. Then you can start doing something to it. So visualizing this then for a tunnel is we have our initialized step, which is super critical. Then we can start to excavate, and then we have to consider our support. And this is a nice simplistic way of looking at the staging of our excavation. So this requires us to set up different stages in our model to think about how we will simulate the excavation process. So we start with our initialize. Okay, that's good. That's nice and straightforward, super important, but straightforward. Then we have the excavate and the support. And how do these relate to each other? Now, simplistically, we might say, we take the material out of the center of our excavation. Boom, we've excavated our tunnel because that's what we see. We take the rock out, and then we install our support. So you would think that this is the most appropriate way of modeling a tunnel, but it's not. The reason is that we know from measurements and analytical solutions that have been developed over many years, that deformations ahead of a tunnel, or deformations associated with excavation, begin ahead of the tunnel face. And this is called the longitudinal displacement profile, is what this function here is called. And there's a number of analytical solutions for it. It's been verified with monitoring using the extensometers. It's been verified using numerical software. And so we've got a really good grasp on this behavior. And what it says is that if we look at, this is distance from the face, so 0 meaning this is the excavation face. If we're looking at our axisometric model, this point here, if we were monitoring the deformations at this point here, right, we have already accumulated nearly 30% of the total deformation. So this axis here is the percentage, or the normalized deformations. And this is 100% of the deformations up here. And of course, this is 0. So there's no deformations. This is distance divided by the radius. So this is 6 radii, so 3 diameters ahead of the tunnel, no deformation. 4 diameters ahead of the tunnel, no deformation. 4 radii ahead of the tunnel, no deformation. 3 radii, we start getting a little bit of deformation. That's somewhere out here. Well, that's somewhere out here in front of the tunnel face. It's already feeling that the excavation is approaching. And as the excavation, or as we look at the deformation approaching the tunnel face, up to the tunnel face, so as we look at the deformation in this material over here, it increases until we get to the face. The face has already experienced nearly 30% of its total deformation. And then, of course, the deformations increase rapidly at the excavation and then slowly decrease until they reach 100% of the deformations somewhere back here. So that's what this part of the curve is here. So thinking about our excavation then, if we know that a lot of our deformation has already occurred by the time we excavate, and that all of the deformations don't occur right at the face, it takes a little bit of distance away from the face for those to accumulate, then using this method of excavation, this instant excavation method, is not a true representation of the behavior of the material. It's too dramatic, it's too instantaneous. What it's saying is that in stage 1, no deformation. In stage 2, 100% deformation. And then we install our support. But that's not actually how it goes. That's not actually how we construct a tunnel. When we construct a tunnel, we do an excavation. We take maybe 1 meter, 1.5, 3 meters, however good our rock mass is. We take a certain amount of material out and then we support. So if we're applying our support somewhere up here, that means we're applying our support when we've only had maybe 60 or 70% of our deformation. From what this is saying, or what this is saying. Here, 100% of our deformation has happened, and then we apply our support. So what is our support doing? Our support's not doing anything. There's no more deformation happening. So our model is going to say, ah, great, our support is fantastic. Our support is not going to fail. Our support is all intact, but our deformations are huge, right? Because we haven't timed our support appropriately to the excavation and the actual reaction of the material. So what can we do about that? A different way of visualizing what happens to the material is to think about what's called the ground reaction curve. And so this is a different way of visualizing it. Here, this is called convergence, but we can also call that deformation. Convergence meaning that it's deformation of the material radially into the excavation. And this is the internal support pressure. And this is a way of visualizing how much stresses the material in the area of the future tunnel are able to hold. So this requires a little bit of mental gymnastics, but what it's saying is that this material here that's ahead of the tunnel face is not quite holding as much stress as the material that's way out here that's not affected by the excavation at all. So as we move towards the excavation boundary, our stresses go from fully in situ and slowly reduce until they're zero when we actually excavate. So the pressure in our material, or the stress in our material, and we call this support. I mean, the support can be the rock that's supporting itself or the support that we install, is slowly decreasing. And as it decreases, then we have increasing convergence. And what we can do then is use this conceptualization of the process to inform how we do our numerical model. And there's two ways of doing that. First is by modeling our excavation using a pressure. And the initial condition would be that the pressure here, or let's look at it over here, the pressure here is the same as the in situ stress out here, right? So that would be our initial condition. Everything is in balance, the stresses haven't changed. We have an excavation, but the rock mass is represented by a pressure. And if we slowly reduce that pressure in steps, so we reduce the pressure, calculate the convergence, reduce the pressure, calculate the convergence, reduce the pressure, calculate the convergence, we can get an approximate solution to this ground reaction curve. And we can slowly decrease the internal support pressure, which is simulating the advancing tunnel, and then compute what the convergence is. And that means that at some point when we're say at 70% of the total convergence, we can say this is where we're applying our support. Not over here, somewhere over here. Similarly, another method that we can use is either concentric excavation, so cutting out very small tunnel and then slowly making it bigger, although this isn't common at all. The second other common method is to use the core replacement method, which uses an initial condition where the material is filled, and with each individual step, a new material is put in there. And what is changed is that this material is changed to elastic. It's no longer plastic. It can't fail. It will only solve for elastic stresses. And the stiffness of this material is reduced in here. And we do that in a number of stages as well. So we have the initial condition is somewhere over here. Then we reset the pressures. So the pressures are reset to zero and when we replace the material. So reset the pressures to zero. Because this material is less stiff, it deforms and acquires a little bit of pressure from this material deforming, pressing on this, induces a pressure inside this material. And we get this point here. And then we replace it again, set the stresses to zero, and then slowly the stresses increase with an increasing deformation, and so on and so forth until we solve down this, this smooth curve using these individual steps. So then, the way to excavate a tunnel, whether it's a sequential tunnel or a full face excavation, is to stage it. And so here is a cavern, for example, with two stages, a top heading and a bench. And the top heading is initialized with the material in it. And then in this case, this is a stress. So the stresses are reduced over a number of stages. So this is stage 3, stage 7, and finally in stage 10, all of the material is gone. And at some point at one of these stages, which corresponds to the amount of pressure that's been lost at the tunnel face or at the location where the support is installed, then the numerical modeler will install some support. And then the support will start picking up some of the load, picking up some of the stresses and deforming and reducing the total amount of stresses that are happening at the excavation boundary. So then the support is actually useful. It's actually, first of all, being modeled in the way that it's actually installed. And you can actually see that it's useful. You can also see whether the support is going to fail or not. And then similarly then for the bench is also sequentially, the stresses are sequentially reduced to simulate that advancing bench. All right, so that is setting up a model. So all of the different stages then, or things to consider when setting up a model. The next thing to think about is running a model. So depending on the solution or the code that you're using, there are different ways of thinking about running your model. And one of the key things to think about is the stop condition. When do you stop the mathematics? For iterative methods, so finite difference typically is an iterative method. Iterative methods will just time step and take very small steps of incremental forces. Or for example, if we are interested in seismicity, we can apply a seismic signal. In this case, this is to a slope, but we could be doing that. This slope could have a tunnel in it if we were interested in the seismic effects on the tunnel. And a good stop criterion for this would be at the end of the seismic signal, or a little bit later to allow all of the seismically induced stresses to dissipate. So the stop criterion here would be allow the signal to go through and allow all of the seismicity to dissipate. In this case, we're looking at probably a mining adit in a bedded rock mass. And this is a discontinuum code. It's also an iterative code. And so it will just continue stepping. And we can see after a certain number of steps, we can see some deformations. Here we can actually see some separation of the discrete blocks. Here we can definitely see buckling of the blocks, buckling here of the invert. Probably at this point, maybe this is 100,000 steps, maybe this is 500,000 steps, however many steps, the engineer probably says, okay, I've seen enough. I can see what the behavior is going to be. It gives me an idea of what sort of design technique I'm going to use. So I'm going to stop running the model now. So the stop criterion then is when you've seen enough of the behavior to start making design decisions. Matrix solutions, so finite element solutions, typically have convergence criterion. Some iterative solutions can also be testing the unbalanced forces and have a convergence criterion, but most of the finite element methods have this, where they are actually trying to solve until the model stops accelerating. All of the forces on all of the nodes are balanced. And you can say that the deformations can keep going, but they're going at a constant rate. There's no more acceleration. This is part of the matrix solving technique, where all of the forces on all of the nodes are being solved simultaneously. And the model is checking that the forces acting on this node in this direction, in this direction, in this direction are all balanced so that the movement is constant and there's no acceleration. So F equals ma, Newton's law of motion requires the forces to be balanced there for no acceleration to occur. So this is then usually the stop criterion for matrix methods, so finite element methods, for example. And if the mathematics are so complex, maybe the material is so weak, whatever it is about the setup, that it cannot converge, it cannot come to a solution where the forces are more or less balanced, then the code will return a failure. It will say, I have not been able to converge, the deformations are going too crazy, the stresses, I can't get them to even out, to slow down. So you'll get an error message. And the reason is that it's not able to balance the forces. The material is too weak, not because you've input, your input parameters are wrong, although that might be one place to look to figure out why you're getting an error. It might be that your input parameters are much too low and unrealistically low. But if they are a true representation of your materials, then it might be that the excavation you're trying to create in these materials will fail. A finite element code can't actually demonstrate failure because it's a small strain, so it can't actually cause squeezing or full-on failure like a discontinuum code can. What it will say is, I can't converge because the accelerations are too much, things are continuing to accelerate according to perhaps gravity or whatever it is. And that's an indication that your excavation might fail, and you have to come up with some other design solution to prevent that failure of the excavation. So even though an error might be frustrating, it also is giving you information about your system. All right, so now we're rounding the corner then into our engineering judgment. We've set up our model. There's a lot of things to think about. We've run our model. We've thought about our stop criterion, what it means when our model has an error. Then we have to start thinking about confirming our model. How good is our model? How good a representation is it of our problem, of the system that we're trying to represent? So first we have to start thinking about interpretation. What are the things that we should be looking at when we're interpreting our model? So stresses are one of them. Are the stresses reasonable? Do they make sense? Are we seeing some weird stresses happening, maybe in the corners? Are our boundary conditions far enough, or external boundaries far enough, etc.? So we're looking at the stresses. That's the first place I look at, is what do my stresses look like? Does it look reasonable? And this is one of those things that it takes time, takes a lot of experience to say, oh, that looks right, that does not look right. Something else that we can look at is the strength factor. So this is a comparison of the stresses to the strength parameters that have been input. Usually we would do this for an elastic model. You can do it for a plastic model as well, but it'll show you the locations where the stresses are higher than the strength. So the material would fail in these locations. So this is showing, for example, that the stress conditions here, the sigma 1, sigma 2 combo, or the sigma 1, sigma 3 combo, is beyond our failure criterion here for whatever reason, and we have failure. Another one to look at if we're getting into models where we're implementing pore water pressure or groundwater flow. A lot of the software nowadays is allowing us to do that. We've got some nice combinations with flow technology, so that's really great and super useful, especially when we're dealing with porous media or fractured, water-saturated rock masses, for example. So we can be looking at our pore pressures. Where are they maximized? Are they following the material boundaries that we've put in, etc.? We'll also be looking at deformations. So this is an example from a Discontinuum code, 3-deck, where we have a blocky rock mass and we're looking at the movement of individual blocks. Where are they moving? They're moving in the invert, up in the crown. We can be looking at vectors, so arrows that point the direction of movement of our material. Usually it'll be in towards the excavation boundary, but it can be concentrated in certain locations. In this case, this is associated with discrete joints. So here's a joint, here's a joint, here's a joint. So we've got a lot of movement associated with these joints here. We can visualize that in Discontinuum and Continuum codes, looking at either contours of deformation or vectors. Failed elements, when we're looking at a plastic model, where is the failure occurring? So this is kind of similar to the strength factor, but it actually shows us, okay, this element here has failed. It failed in shear, which means that we overcame the Moore-Coulomb failure criterion, or these little dots here, these little open circles, are failure in tension. So this can tell us something about what part of a failure criterion was enacted for this failure. We can then compare that to the stresses, to the displacements. So we have a lot of displacements here associated with these tensile zones, not a whole lot of displacement here associated with these compressive zones, etc. So we can start looking at where we're expecting failure and start targeting our design then to deal with those failed materials. When we're installing support, then we can also visualize how the support is doing. We can look at the failed portions of the support, and we can also be plotting things like moment thrust diagrams for liners to see whether or not we're going to be expecting cracking in certain portions of our liner, and we're overcoming the failure criterion of our liner. So those are also important things to look at. Bolts, anchors and bolts, looking at what sort of failure we're expecting in our bolts. So this model, for example, there's tensile failure of all of the bolts. So all of these bolts are not being used anymore because they've all failed in tension. So that then tells us, okay, our design is insufficient. We need to do something about our bolts or maybe our liner or some combination. So these are just a few of the most important things that we'll be looking at for our interpretation from both our material behavior and also interpreting our support. So this moves then to model confirmation. And we need to be thinking about, we're doing this at the interpretation stage, so we'll be looking at all of the various aspects of interpretation and doing what's called verification, validation, calibration. And all of these can be lumped into confirmation. How good is our model? And there's a really good quote that I like to say is that all models are wrong, but some models are useful. And what we're trying to do is we know now, the mathematics, the discretization, the constitutive models, the stresses, the stiffnesses, all of these are simplifications, which means that inherently our model will be wrong. It will never be a true representation of our problem. But if we do a really good job of setting up our model, we understand how the mathematics and the limitations work, we use our engineering judgment, then we can get as good a model as possible to help us make design solutions. And this is where models are useful, but we have to be careful. We have to go through this checking process to make sure that our model is as useful as possible and to eliminate as many errors in our model as possible. So there are a couple of different ways of doing this. One is to compare our numerical model solutions to analytical methods. So here's an example of a circular tunnel showing the different stress conditions around the tunnel. We can compare that to the closed form Kirsch solution, for example, which allows us to compute radial, tangential, compressive stresses and shear stresses. We can compare to observed behavior. So here is a fractured rock tunnel, and we could observe failure along our, in this case, this was foliation. So failure of blocks along the foliation in the sides of the tunnel. And we actually observed that always on the left-hand side of the tunnel, we could observe that. And we were able to see that the majority of the deformations were on the left side of the tunnel. So this gave us a good feeling that we had a reasonably representative numerical model. So those two main ways then, either looking at analytical solutions or looking at ground behavior that we can observe, are two of the most important ways of confirming our model. Making sure that the model, in addition to that, or part of that, is checking to make sure that the way we've set up our model is appropriate. So for example, are the boundary conditions far enough? Also checking that our material parameters are reasonable. Did we put in the joints in the right orientation, or are we getting a lot of failure around a tunnel, but we're not actually seeing it? Or is our slope falling down, but we can look out the window and the slope is still up on the mountain? So all of these things help us identify whether our material parameters are too high or too low or just right, whether our mesh is appropriate. So if we're seeing weird stress concentrations, sometimes that might be because of the mesh and not anything to do with the model or the system itself. So we're constantly having to check these things. So validation then is, or verification is then checking that the setup of the model is right, that our boundary conditions are okay, that our mesh is okay, that we don't have some weird mathematical or geometrical issue in our model. And we can see that when we look, for example, at the stresses. Our stress contours are nice and smooth. We don't have weird concentrations in the corners. We don't have a weird concentration out here that makes no sense from a geological perspective or an excavation perspective. So checking that that the setup of our model is appropriate. The validation then is checking that our model is able to simulate either analytical solutions, so simple analytical solutions, or able to simulate a true behavior that we can observe. So is the model doing what we're expecting it to do? Is it a valid simulation of our system? And then finally, calibration is all of the input parameters, the stresses that we've put in, the material properties, whether that's the geological materials and our support materials, are all of these parameters reasonably close to what we have in our system? And that also requires a little bit of engineering judgment in terms of, you know, if we're in a rock tunnel, a fractured rock tunnel at shallow depth, and we're seeing a tremendous amount of failed elements, then we might be thinking, I don't think my material properties are quite right. A rock mass at 20 or 50 meters depth shouldn't be having a whole bunch of failed elements in the crown. So then you go back to your material properties and you see, oh yeah, I put 5 MPa instead of 150 MPa for my UCS. So you can find that there's an error. Or maybe you go back to your lab testing and you see that, oh, the lab testing wasn't actually on the right material, or whatever it is. So it's that calibration. And then also with the stresses, right? Making sure that the stresses are properly calibrated. Are they too high? Are they too low? Are they in the right orientation? This, for example, is a situation where we have vertical stress is the highest and the horizontal stress is the lowest. And we can look at the stress vectors here that show us that. And our stress concentrations are here on the sides. So we would expect shear failure here on the sides, and we would expect a little bit of tensile failure here at the top and bottom. When we're in our tunnel, if we're seeing that we have a lot of shear failure here, and tensile failure here and here, that's probably because our stresses are actually oriented a little bit away from the vertical, like this and like this. So we need to rotate our stresses. So stress magnitude and stress orientation also need to be calibrated, and normally with observation. Now, of course, if we're in a green field and we don't have a tunnel to compare with, we have to be using different methods to do that. Maybe using another case study to validate our model, to calibrate our model, or using other experiments like modeling a UCS experiment to say, okay, yeah, my input parameters are the same as my lab results, so I can use those material properties in my model. So that's the calibration stage. So then the final bit is sensitivity analysis. So once we've confirmed that our model is reasonable, it's a useful model, it's the best model that we can make with the tools that we have, we can move on to then doing a sensitivity analysis, which is the main part of our design process. And this is what then triggers a change and the looping through of our loop. We do a little bit of sensitivity analysis when we're doing our confirmation. If we have to change our boundary conditions or our mesh, for example, then we might be, changing our boundary conditions a few times, rerunning. And then once we're happy that the model is confirmed, we do a sensitivity analysis specifically for design. So there's a couple of different things that we're doing for a sensitivity analysis. The first would be linked with confirmation, like I already talked about. And the next is dealing with the fact that we're simplifying our model. So we're simplifying the material. The material that we're dealing with natural materials. We know that there's a lot of variability. There's a lot of uncertainty in the parameters that we're putting in there. We're simplifying the model, we're simplifying the geometry, we're simplifying where our material boundaries are. Usually we'll take one cross section that represents hundreds of meters worth of tunnel, but that one cross section will not always be a true representation of every single meter advance that we do along that 300 meters length, for example. So what we're trying to do there is to see what the impact of each of those simplifications is on our results. So if we say, okay, I'm going to change the Moore Coulomb parameters a little bit, I'm going to make them a little bit weaker, I'm going to make them a little bit stronger, what does that do to my deformations? Does that make a big difference? Is it really important for me to have super high precision for my input parameters? Or am I generally in the elastic realm anyways, so it doesn't really matter what they are, it's not super important. What's actually important is something else. So we're trying to identify the key parameters that are important. We're also trying to say, if we know that we have variability, sometimes we're in a better quality rock mass. So for example, our granite is more weathered and less weathered in certain places, then maybe we have an upper bound condition with the unweathered granite and a lower bound condition with the weathered granite. And then we would do a sensitivity analysis. How much does that affect our deformations? How much does that affect the loads on our liner? What do we need to do for our sequencing? Do we need to do a split heading, for example? So then we use that sensitivity analysis to look at what happens when we change those parameters, what happens when we encounter different conditions during the construction. And that can then be used to say something about the entire system, the natural system, as well as the engineered system that we're putting in there, how all of those parameters are working with each other to then come up with our best design. Right, so some of the things that we can do with a sensitivity analysis are simplifying the model. So looking at what the effect of mesh size is. So if we increase the mesh size, then we reduce the number of elements we're solving for, our runtime is shorter. Does that actually affect our results, or are results much worse? At what point can we say, yep, the mesh size is optimized? Our input parameters, so here's an example of a spider graph showing if we change friction angle, cohesion, density, and seismicity, for example, increase them and decrease them, what is the impact on, this would be for a slope, for example, what is the impact on a factor of safety as we change all of those? Which one has the highest impact? Friction angle obviously dominates the factor of safety, so it's really important to get a good handle on friction angle. Seismic acceleration, not so much in this case, so we don't have to be quite so precise, quite so pedantic about getting exactly the right accelerations. Here's a way of looking at the sensitivity analysis using a tornado graph. So again, if we have some change or some change in our material properties, so maybe it's the stress anisotropy, pore pressure, the shape of, this is a well, for example, a geothermal well, the shape of our well. What happens when we change all of those things on the ultimate strength of the sides of the well, so the ultimate stability of our well? So in this case, it looks like stress anisotropy is the most important parameter, whereas the shape of the well is not that important in this case. So this is another way of visualizing those sensitivities. And then using sensitivity analysis then for our design is not just for looking for the best design. So what happens if we make our rock bolts longer or our shotcrete thicker or whatever it is, but it can also be used for determining our monitoring thresholds. So if we have a deformation threshold warning level, so we say, okay, if we have deformations less than 5 millimeters, we're green. If we have 5 to 10 millimeters, we're yellow. 10 to 15 is orange. Greater than 15 millimeters is red. And normally we'll have a warning level. We'll have different things that we need to do at each of those warning levels, stop construction, etc., redo our numerical models, whatever it is. How do we decide what those values are? How do we decide whether it's 5 millimeters or 7 millimeters, the trigger between green and yellow? Well, we can do a sensitivity analysis by progressively weakening the material, or by progressively adding joints, or by progressively increasing the stress, or whatever it is that we think is important. We can change the stiffness of the material, for example. Here are two examples. This is K0, so this is the vertical to horizontal stress ratio, and this is the stiffness of the material. So as we change either of those, what does that do to a deformation? That can then help inform what our trigger levels will be. So this is a way of using sensitivity analysis then specifically for our design. So that ends then our whole cycle of design, because then, of course, once we're looking at the sensitivity, we go back, we change our model, and we come back through the entire loop. And that, in a little over 2 hours, is a summary then of best practice for translating a tunnel problem, a tunnel system, into a model, and all of the different steps and considerations, a little bit about the mathematics, a little bit about how to use your engineering judgment to pick different aspects, to address different aspects, the uncertainty, the simplification, etc. So that when you go to use a numerical model, a numerical software, you're hopefully moving beyond using it as a black box, clicking the buttons. It's so easy to click the buttons nowadays and produce something beautiful, but inherently meaningless, unless you're thinking very deeply about all of the different steps, including all of the mathematics that's running in the background that's invisible to you. So that was the aim of today, and hopefully we've gotten there with this, this reasonably short visit through numerical methods for geotechnics. So I think we've just got a couple more minutes, so I'll hand it back to our host.
Yeah, hi, thank you. Any questions? Participants? Or you can write us directly later as well for your questions and queries.
Hi, my name is Pawan. I'm from GZ Consultants. So we are working on the trigger values, what you have already discussed. So we already faced so many issues with those trigger values. Those are very small or which are not practical at this site to implement. So in that cases, what is the best way to judge a trigger value? Is that a deformation is the better way, or to go for a strain gauges is a better way? So how to judge in numerical modeling?
So from the numerical modeling perspective, obviously you can be looking at both from the, you can be looking at the strains at any point in your numerical model, and you could be relating those to strain gauges. It's actually an interesting engineering question that Robert in some ways would probably be better suited to answer, whether you would use deformations or strains, because of course from a numerical modeling perspective, you can measure any of those as an output to help inform your trigger. But if your deformations are really small in your numerical model, then that becomes an implementation issue, which I don't know if Robert has any input on that.
I mean, from my perspective, we are trying to do everything based on deformations, because this is the only thing which we can really measure. I mean, we try to measure strain stresses also on site, but to have most realistic calculations, we try to figure out what are the deformations and go back from the deformations to the stresses. This is the way which is most practical from my point of view. Of course, the other way around would work. I mean, look at the material behavior of shotcrete. What complicated material laws we in reality would have to use for just this simple material. Fact is, what we can measure is deformations, and what we can try to find out with the calculations then is what is the stress in the system. This is my opinion.
Okay. Because here where we are facing the problem is that the intersections between two tunnels. So rest of the conditions are fine, but wherever the intersections are coming, because of it is a stiff system, we are getting very less, means we few mm, like 2-3 mm of deformation, which is not practical to measure at this site. So that's why we are confused with what to follow. So you're saying that strain gauges or stress gauges would be better, stress cells or load cells?
No, that's I'm not saying. Of course, they are existing. I'm relating to deformation monitoring with the mirrors which you use. But to be very clear from my perspective, what we can do with numerical calculations, as Marlene really showed, is we have a lot of simplifications in these models. Okay. We can get an idea. We can get an idea, but never an exact result. What will happen? So in a let's say pre-feasibility study, or I don't know in which stage you are with your project, you can just get an idea. Okay, should I subdivide in top heading range, or can I do a full phase? So these ideas you will get from the numerics, but you can never, in my opinion, or in I think in our opinion, you can never get an exact result. So your calculations always have to be followed by geotechnical monitoring results, and you compare. And now my point is the comparing is more easy to do it with deformations, because I'm measuring deformations. In a pre-feasibility study, it doesn't matter how which direction you go, because you are not building something. You just want to get an idea, let's say distance of the two tubes. What is a good distance, not to have an influence between the two tubes, or intersections. What will happen in principle? When you are then going into the detailed design, let's say when you are starting the construction, situation is that you would like to follow what you calculated by measurements, and vice versa. This is my statement to that question.
Okay, thank you, Robert. I got that. Thank you, Marlena. You've given a very good presentation, and really opened up a few of the things regarding the sensitivity analysis. So that's a very nice ideas you have given to us, so we can follow up in our design to update the things better way. Thanks both of you for giving this nice lecture. Thank you.
Thank you.
Any other question?
I think everything was clear, and
Yes.
I think we can close the session. And I also thank Marlene for doing it.
Before closing, I would like to express my sincere gratitude to all the participating members in today's virtual training session, and special thanks to Lieutenant General Suresh Sharma and Dr. Robert Galler. And I am very thankful to Professor Marlene for sparing her valuable time for conducting today's program. I'm sure all the participating members have benefited from her vast experience and knowledge shared during the program. Thank you so much. Stay safe, stay healthy. Thank you.
Same to you. Thanks a lot. See you soon.
Thank you.
Ciao.
Bye.
See you soon.